Thank you, everyone, for being here. Thanks for taking the time. And also, thank you very much for inviting me and for being so welcoming. As Aaron mentioned, my name is Michael Conrardy. I've been working on greenhouse gas issues and offsets since 2010, and I'm here to talk about offsets today. But before we get into the details of offsets, I wanted to provide some context in this upfront section so we get an understanding of why it is we're talking about offsets in the first place. So this upfront section we're calling Greenhouse Gas 101, and the major driver for being interested in greenhouse gases in the first place is climate change. So very briefly, what is climate change? Climate change is the change in global or regional climates, and the most important part about this too to understand is that it's due to human activity. The climate does change, but when we refer to climate change, we are in fact referring to the human actions that are rapidly changing the climate. These human interactions are the emissions of greenhouse gases, which warm the planet. So this isn't new. We've been studying the climate as a human species since at least the 1800s. The issue of climate change, as previously defined, has been around since at least the 1950s. Warnings of climate change were being put forward, with the earliest publication in a national document in 1979, testimony to Congress in 1988, and then further getting into the Internet Governmental Panel on Climate Change was formed, which is comprised of hundreds of scientists throughout the world. These scientists have been working for several decades, putting this information together in this literature. It's a well-documented thing. The most recent report out of the IPCC is known as Special Report 15, or SR 15. And what this report does is it gives us a pathway by which to bring greenhouse gases to a level to where we can keep warming within what is considered a safe range. So that warming in a safe range is considered 1.5 degrees Celsius. This is what international governments have agreed to. This is what scientists generally state as a safe level of warming. And this SR 15 shows us the pathways that we need to maintain that. There are a lot of details up here, a lot of information on this slide. The one thing that you need to take away from the slide is just the shape of that graph. This is the ultimate goal. This is all the ultimate pathway. So why do we care? Climate change is not something that we are worried about in the future, but we are worried about right now as well. There are impacts all over the world. Here in Hawaii, your sea level rise is affecting water tables and fresh water. Erosion is happening. You have drier seasons, which may disrupt agriculture. You have acidification of the oceans, which causes coral bleaching. There's many other species that are affected by this. I could go on and on this point. But the main thing is, this is why we care. This is what we're interested in. This is what we're aiming to avoid. We don't want this to get much worse. So how do we do it? You can't manage what you can't measure. So this adage has been used over and over to really begin the process of understanding various things. This is part of the process to understanding climate change as a problem. It's also part of the process to understanding the solutions. So we need to understand how we calculate and measure greenhouse gas emissions in order to get on that pathway, again, from that curve that I've asked that you keep in mind. So how do we measure greenhouse gases? What are greenhouse gases? So greenhouse gases have been measured in their concentrations since here in Hawaii at Mauna Loa since about 1960s. That's one of the most famous locations for measuring concentration of greenhouse gases. There are other locations measuring greenhouse gases all over the world. These measurements are consistent, constantly being assessed. 350 parts per million is the concentration of greenhouse gases that scientists believe is a safe level. of concentration of CO2. Some of the most recent measurements off Mauna Loa, I pulled this last week, is 411 parts per million. Never since human species have existed has the concentration of CO2 in the atmosphere been this high. So this is part of the science that leads into that climate change. This is the ultimate goal that we're interested in getting at. How do we decrease this concentration? So many of you may have heard of greenhouse gas emissions being assessed through tons. So how do we go from parts per million to tons? The way we do that is we understand various aspects of the atmosphere, various details of the Earth, and we can convert this concentration into what we call carbon budgets. There's many ways to define carbon budgets. There's some numbers on this slide. And so these numbers are based on a very specific definition of carbon budgets, which is written on this slide. So basically, these numbers are how many tons of greenhouse gases could we as a human species emit up into the atmosphere to avoid 1.5 degrees centigrade. Not just avoid getting past that point, but having a 66% chance. So we're very precise in the way we talk about these things. And the estimates from the various scientific communities that are measuring this is that we have left anywhere from negative 190 approximately to just over 700 gigatons. You don't have to worry about what a gigaton is. And additionally, I had mentioned the IPCC earlier, so I wanted to point out that their measurements are somewhere in the middle of this range. But this is the range that essentially every scientist has put forward. The things you need to understand about these numbers is the negative number. So what does the negative number mean? The negative number means we may not have the chance to keep it below. That's where we are today. More optimistically, at that higher end, 779. If you were to divide that equitably among all the people on the planet, you then have just over 100 metric tons that we can each emit within our lifetimes to ensure that we have a 66% chance of maintaining below 1.5 degrees. So that's the equitable distribution. So here in Hawaii, this is very common in the US, also in Europe, the approximate per capita emissions is about 15 tons a year. So at the rate that folks in Hawaii and California as well, the US are emitting, we have less than a decade before we hit our equitable distribution of the rest of the carbon budget. So this is what carbon budgets look like. This is where we're at. And the good news is Hawaii is taking some action, right? So you guys have passed legislation towards carbon neutrality. And if you guys were able to maintain that, you could get this 15 per person down. And this is an achievable thing. So the whole point right now is to talk about how we're calculating these things. So we've gone from climate change to parts per million to carbon budgets. So how do we then get this 15 tons? How do we get how much we're emitting from our institutions? We have to understand the gases that we're dealing with. So CO2 is the dominant gas among the many greenhouse gases that humans emit. It's the dominant warming force of all the greenhouse gases that humans emit. But there are other gases. This is a graph from NOAA. What you can see on this graph, and the thing I want you to take away, is that blue line is the representation of the warming that's attributed to CO2. And the other lines is when you add in other greenhouse gases. So there is a gap there, or a delta, sometimes we refer to that as, that demonstrate basically the difference between what is happening with CO2 and what is happening with these other gases. So what are the other gases? The dominant, regulated, and assessed gases are these 6. There are other greenhouse gases, but these are the 6 that are typically within an inventory. Carbon dioxide, methane, nitrous oxide, hydrofluorocarbons, chlorofluorocarbons, and SF6, or sulfur hexafluoride. One thing that I want to note about these gases, and one thing I also want to note, is the difference between greenhouse gases and carbon. Colloquially, greenhouse gases and carbon are often synonymously used, and I actually think that's okay. I think that's a fine thing. We need to understand these things on specific terms, but so when we talk about it, we talk about carbon, we talk about greenhouse gases, using them synonymously is not really much of an issue. As you can see by the chemical formulas from these gases, more than half of them contain carbon, which is represented by the C in the chemical formula next to them. So it really is this carbon that's the driving force, particularly as CO2, as previously mentioned, is the dominant emitted gas by humans. And the other thing about these, and the reason partly why using those terms synonymously is okay, is that we always bring these terms back to CO2, or what we call CO2 equivalents. So each one of these gases has what's called a global warming potential, and the global warming potential varies among these gases. And in the simplest terms, global warming potential is basically a combination of the radiative forcing, the heat trapping ability of that gas, and the atmospheric lifetime of that gas. So how long does it stay up in the atmosphere? So global warming potential is meant to capture those two areas. When you see global warming potential written without a time frame, you are almost always looking at a 100-year time frame. But we can look at global warming potentials at various time frames. We have 3 listed up here. But what's most useful for inventories is to really start to simplify that, bring it down to one thing that we can constantly look at. So 100-year time frame is considered a pretty appropriate way to do it when you're conducting an inventory and starting to calculate these total emissions. So once we know the gases, we also need to know the sources that these gases come from. So energy is the dominant source of all emissions. And by energy, typically this is fossil fuels. This is the main driver of energy. When you see greenhouse gas inventories, you will inextricably always see energy as one of the, if not the highest emission source for any entity. At state and national levels, you'll often see transportation summed up under energy as part of that sector. If you do conduct greenhouse gas inventories for smaller entities, you'll very often see transportation separated out. But at national and state levels, transportation is included in this. This is meant to be basically, in the simplest terms, the sum of the emissions from fossil fuels that we do use to dominate our energy sector. So beyond energy as a source, we have the industrial processes. Here in Hawaii, there aren't a lot of industrial processes. Other places, industrial processes dominate their inventory a little bit more. Cement is a big industrial process. Used to be some, I believe, in Hawaii. And there are other processes where manufacturing, making other goods. So industrial processes includes those kinds of things. The other thing that it includes is electric distribution. So in order to distribute that energy, often the gas SF6, which was previously shown, which is the highest global warming potential gas of all of the regulated gases, at about 24,000 times the global warming potential of CO2, as was previously mentioned on the slide. SF6 is used in these electric distribution systems. It does not have to be used. PG&E in California has made commitments to phase out SF6 completely. Many power plants have done so. But SF6 is part of this energy distribution, the dominant part. The other thing is what's called substitute of ozone depleting substances. These are comprised of the hydrofluorocarbons that was listed as one of the groups, one of the 6. These are basically used for refrigeration systems. So this is what these processes look like. Then you have basically land use. Land use is a source of emissions in one regard. This is the land use of soils, agricultures, forest fires, and the like. So when these things occur, forest fires, for example, you have ultimately emissions of greenhouse gases into the atmosphere. When you manage livestock, there's manure, these kinds of things, and you have methane emitted into the atmosphere. So land use is in fact a source of emissions. But on the other hand, land use is also what we call a sink, where carbon is sequestered, in another word. Or in another word, basically CO2, the carbon within the CO2 is taken out of the atmosphere and pulled into either the soil or the plants. The dominant feature here in Hawaii is the forests. You'll hear more from a group later talking about carbon sequestration in forest, but the carbon sinks in Hawaii actually, within land use, outweigh the sources themselves, as you'll see when the Department of Health comes up in a moment here to share what the ultimate inventory for the state of Hawaii is. Now, the last major category where we add up these emissions sources is waste. So this is landfills, wastewater treatment, compost. The gases here are actually methane and N2O. No CO2 is attributed to these sources. There's something called biogenic emissions, which some of you may be familiar with. But basically, we don't end up counting those in the same way. So within the waste sector, methane and N2O are the dominant emitting gases that are emitted. So these are the sources. I talked about the gases. I talked about the parts per million. I talked about the climate science that needs all those things. And we also then need all these things to inventory so we can get along that path that the IPCC put forward. So we need to add this all up into an inventory. And in order to do that, we use inventory methodologies and protocols. There are many methodologies and protocols that exist that are out there. The IPCC has a framework that is regularly used. The top three protocols that are listed here, the IPCC and two from the EPA, are the methodologies that are used to conduct the Hawaii state inventory. The methodologies and protocols are essentially a roadmap or instructions on how to take all of the things that I just said and pull them into a number where you can say, this entity, this group, this state is emitting this much CO2 equivalent of greenhouse gas emissions. The last bullet here is another dominant greenhouse gas protocol by WRI and the World Business Council on Sustainable Development. It's simply called the Greenhouse Gas Protocol. It's regularly used for smaller entities, businesses, cities, and the like. And so I wanted to include it here, even though this is not, I do not believe what the state of Hawaii uses. I wanted to include it here because if anybody in the room is familiar with greenhouse gas inventories, this is one of the dominant protocols used. And with that, I also want to mention scopes. So scopes are an important part of greenhouse gas inventories. The primary and simplest way to describe scopes is that scopes are intended to distribute responsibility of greenhouse gases. Many people don't put it that way. Many people talk to you about what each one of the scopes are. I'm not going to get into scopes because at the state and national level, scopes aren't typically used. You usually have a large enough organization that attributing that responsibility between the scopes is not needed. But if you are familiar with greenhouse gases, you probably invariably have heard the word scopes, and I would be very remiss if I had not mentioned it to you, because you might wonder, why didn't he mention scopes? And the reason is, again, at the state and national level, this isn't the way that we typically refer to these things, though it is an incredibly useful way to look at greenhouse gases, particularly from smaller agencies. And so it is a way that folks will use them, but because we're talking about the state, this will be the last mention of scopes here today. And that actually wraps up the GHG 101, the context of all of this. And I'd like to, at this point, invite up Mike Madsen from the Hawaii Department of Health. Mike's been an environmental engineer for over 20 years, and he's been working on the inventory here for the state of Hawaii. So he'll be able to basically take all the information that I just shared and tell you what the results for the state are. Mike's been really useful in this process, and we're very, very grateful to have him here. So, Mike.